Penuh ya?
Penuh, Pak.
Penuh, Pak.
Pertemuan kedua ini terkait dengan capaian learning objective yang pertama, ya. Terkait dengan capaian learning objective yang pertama, yaitu diharapkan mahasiswa itu mampu memahami peran rekayasa dan desain, ya, dan aspek-aspek dalam rekayasa. Pada pertemuan pertama, kita membahas peran rekayasa dan desain, ya, yaitu dua topik pembahasan waktu minggu lalu, peran rekayasa dan desain dalam masyarakat, dan profesi insinyur, orang-orang yang berperan di sana, membentuk dirinya menjadi profesional. Itulah pertemuan pertama. Pertemuan kedua, pokok bahasannya adalah aspek-aspek dalam rekayasa. Ya, aspek-aspek dalam rekayasa. Sehingga kita hari ini, ya, pokok bahasan pertemuan kedua ini adalah dari capaian learning objective yang pertama itu, yang aspek-aspek dalam rekayasa. Ya. Sekalian mereview, sekalian kita mengingatkan kembali kemarin, ini terkait rekayasa. Orangnya disebut rekasayawan, engineering, ya, orangnya disebut engineer, ya, dalam dua bahasa. Apa itu engineering? Apa itu keteknikan? Adalah bidang dalam pekerjaan ilmiah yang melibatkan pengambilan pemahaman ilmiah kita tentang dunia alami dan menggunakannya untuk menemukan, merancang, dan membangun berbagai hal untuk memecahkan masalah dan mencapai tujuan praktis. Ya, bagaimana kita mengenali masalah? Ya, era sekarang masalah pun bergerak maju. Bahkan bagaimana kita menduga adanya potensi masalah. Adanya potensi masalah. Sehingga kita memberikan alternatif-alternatif solusi untuk mencapai tujuan-tujuan praktis. Sederhananya, engineering adalah teknik, yaitu aplikasi sains untuk memecahkan masalah dunia nyata. Jadi, solusi sains, solusi sosial, bagian dari solusi engineering. Artinya seorang engineer tidak cukup melihat solusi itu dari solusi engineering saja. Harus mempertimbangkan solusi sains dan solusi sosial. Ya. Ada top 20 produk engineering di era sekarang ini. Ya. Ada 20 elektrifikasi, ya. Kemudian yang terkait dengan elektrifikasi itu apa sekarang? Ya, yang minimal lah, yang dulu orang sumbernya sudah beragam sumber energi, ya, di engineering, ditiru orang, ya. Salah satu sumber energi yang paling ya nuklir, yang paling besar, ya, tapi ada bahayanya. Oke, otomobil, ya, bagaimana mobil listrik? Nah, bayangin aja sekarang kombinasi antara elektrikal dengan mobil, keluarlah mobil listrik. Ya, bagaimana mobil listrik berlomba sekarang? Ya, ibu kota negara baru itu semangatnya adalah tidak ada pom bensin, agar ada perlombaan di mobil listrik. Jadi kita mau loncat, Indonesia mau engineer Indonesia mau loncat, ya, kombinasi mobil dengan listrik, mobil listrik diterapkan di ibu kota baru di Kalimantan sana dengan tidak membuat adanya pom bensin, kebijakannya mendukung. Nah, itu kira-kira perkembangan yang sangat dahsyat terakhir ini. Ya, pesawat, ya, juga berlomba, ya, bagaimana kecepatan, terutama dikombinasikan dengan telekomunikasi, IT, ya. Bagaimana sebuah pesawat itu sekarang nyaman, tidak cukup hanya nyaman dari sisi makanan apa segala macam, kebutuhan berinternet pun, ya, sudah dimampukan di angkasa luar. Kemudian, ya, terkait dengan air bersih, ini kan problem nih, dan distribusinya, elektronik, ya, banyak hal, radio, televisi, ya, mekanisasi dari hasil pertanian, Bagaimana komputer sudah jelas, telepon, ya, telepon dengan mengarah kepada ya suara, gambar, ya, suara, gambar dan video bisa dihantar bersama-sama. Era sekarang era fit call, ya, karena kombinasi. AC ya berkembang terus. Apa yang AC berkembang itu selain dari kapasitasnya, tapi energinya. Jadi bagaimana menciptakan suatu AC yang low energy, ya, low energy dan healthy, ya. Jadi banyak nilai-nilai tambah karena pekerjaan engineering, ya. Spacecraft, ya. Internet sudah jelas bagaimana Internet of Things, segala benda sekarang itu thing itu menjadi punya address untuk bisa mengirimkan informasi, data-data, Internet of Things, ya. Benda yang tadinya benda mati sudah ditempelin internet di setiap thing, sehingga dia menjadi sumber data, ya. Bayang sekarang kalau di gigi kita nanti itu ada chip, ya, yang bisa memberikan data-data konsumsi makanan kita, kesehatan kita, gigi palsu, ya, Internet of Things, kenapa tidak? Nyambung ke data kesehatan kita, ya. Maka ini akan semua salah satu yang berkembang itu healthcare, ya. Healthcare sangat berkembang, ya. Kemudian peralatan rumah tangga, ya. Peralatan rumah tangga berlomba, jadi tidak lagi hanya perusahaan-perusahaan besar yang berlomba di peralatan rumah tangga, ya. Sistem transportasi, ya, fiber optik, ya, dengan bagaimana teknik modulasinya tidak hanya menciptakan perangkat-perangkat aktifnya, ya, tapi juga dari sistem telekomunikasinya. Nuklir hubungannya dengan energi, ya, material, ya, penciptaan material-material, ya. Salah satu material tambang yang diperebutkan dunia saat ini adalah nikel, karena nikel menjadi sumber energi yang bisa menyimpan energi dengan dimensi yang kecil, ya. Berlomba orang dimensinya kecil, tetapi kapasitasnya besar. Artinya kinerja material itu tinggi. Engine berasal dari bahasa Latin engineering, menciptakan, kemudian orang merancang hal-hal kreatif sebagai engineer. Oke. Kata engineer, ya, mengacu kepada orang kreatif, cerdik, yang memenuhi solusi untuk masalah praktis. Ya, itu harus melekat. Kalau disebut engineer, maka ada karakter kuat di sana, yaitu karakter kreatif dan inovatif, ya. Dua karakter yang muncul ketika kita menjadi bagian dari engineering, orangnya disebut engineer, maka akan ada karakter yang tumbuh. Harus ada kesadaran kepada orang itu untuk menumbuhkan suatu karakter, dua karakter penting, yaitu karakter kreatif dan karakter inovatif. Sehingga solusi-solusi yang tadinya tidak mungkin bisa dimungkinkan dengan penciptaan dan kreativitas dan inovasi-inovasi yang bisa menghasilkan suatu solusi-solusi yang mungkin. Ya, dengan adanya prinsip yang dia miliki, prinsip keteknikan, ya, memecahkan masalah itu dengan prinsip, ada landasan yang kuat, ya, landasan sains sendiri kuat, jadi bisa dibuktikan secara matematis, ya, menghasilkan suatu inovasi, melakukan suatu kalkulasi, identifikasi masalah, tapi dikuatkan dengan bukti-bukti. Jadi sebelum melakukan rancang bangun dalam bentuk wujud nyata, maka dia sudah melakukan kalkulasi, ya, kalkulasi kekuatannya. Kalau tidak, ya kebayang korbannya sebesar apa. Nah, itulah kenapa keteknikan itu basic sainsnya harus kuat, prinsip-prinsip dasarnya kalkulasi harus kuat. Sehingga seorang engineer memiliki karakter yang harus ditumbuhkan tadi, kreatif dan inovatif, ya. Mereka sesuatu yang punya seni. Jadi seni bagian dari ya bagian dari seorang engineer, ya. Seperti Isaac Asimov pernah berkata, dia sains dapat menghibur dan mempesona kita semua, tetapi tekniklah yang mengubah dunia, ya. Jadi untuk memperkaya ya sains, tapi yang mengubah itu adalah engineering. Hampir semua yang kita lihat di sekitar kita telah disentuh oleh seorang engineer. Ya. Engineer adalah orang kreatif yang menggunakan matematika, prinsip ilmiah, sifat material, dan metode komputer untuk merancang produk baru dan memecahkan masalah manusia. Engineer dapat melakukan apa saja, merancang dan membangun jalan, jembatan, mobil, pesawat, stasiun luar angkasa, telepon seluler, komputer, peralatan medis, dan banyak lagi. Ya. Dunia ke-engineering juga sangat luas. Ya. Aerospace, agriculture juga masuk, otomotif, ya. Biomedik, sipil, kimia, komputer, ekologi, ya, elektrikal, ya, geologi, manufaktur, ya, kelautan, teknik nuklir, teknik transportasi, ya. Dan akhirnya berkembanglah program studi keteknikan. Ya. Nah, rekayasa dan desain ini untuk minimal mengetahui luasnya bidang keteknikan, ya, tetapi kita mendalami satu disiplin untuk bekal, ya, bekal ke depan menjadi engineer yang profesional. Nah, ruang lingkup semua itu sambil ya minimal gambar besarnya dapat. Jadi kuliah kita mungkin tidak akan mendalami sedalam-dalamnya, tetapi menggambarkan bahwa ruang lingkup, ya, kalau minggu lalu kita mengilustrasikan seperti huruf T, maka seorang engineer harus memahami ruang lingkup minimum ruang lingkup dari pekerjaan engineer lainnya. Ya. Contoh aerospace engineer, itu perannya apa? Ya, mereka berperan menerapkan prinsip-prinsip ilmiah dan teknologi untuk meneliti, merancang, mengembangkan, memelihara, dan menguji kinerja pesawat sipil dan militer, rudal, sistem persenjataan, satelit, dan kendaraan luar angkasa. Mereka juga mengerjakan berbagai komponen yang membentuk pesawat dan sistem ini. Biomedic.
So I'm Trevor Jones. I work here at the NASA Glenn Research Center, which is in Cleveland, Ohio. I'm an aerospace engineer. An aerospace engineer is similar to a mechanical engineer, except for the focus is more on space applications and aero applications, which basically means airplanes, anything that flies, helicopters. So I do a lot of things such as designing spaceflight hardware, launch vehicles, analyzing them using the computer, and also doing testing like we are here in the vibration test lab. So this is one of our large vibration shaker tables. So what we'll do is put a piece of hardware on here, and then this whole table actually shakes to try and simulate the launch of the space shuttle or whatever other vehicle that this hardware is sitting on. For example, we've tested various antennas and things that are going to be going on to the space station to be used for communication. So first they'll come here, we'll connect them to the table, we'll instrument it with different accelerometers, which just measure how the unit is moving, and then we'll shake it, take a look at the data, and if it hasn't broken and everything seems okay, then it'll be okay to go on to the next test before it's eventually launched. Yeah, so I guess one of the neatest experiences I had here was, I spent a lot of time working on this Ares 1X launch vehicle, right? So I started before it was even a real thing. It was just a concept, working on teams to design what the vehicle was going to look like. And I guess just the neatest and humbling thing was when it was actually built and seeing the hardware and seeing how big it was, and then actually watching the thing launch and watching it work as we expected to. That was really a rewarding experience for me. It's hard to describe. I went to Rensselaer Polytechnic Institute to get a bachelor's degree in mechanical engineering, which I have. From there, I got a job here at NASA and continued my education here at NASA part-time at Case Western Reserve University, where I got a Master's of Science degree, also in mechanical engineering. Okay, so when we were designing part of a vehicle recently, we had an issue where some of the delicate electronics, computer hardware and stuff that was on the launch vehicle were experiencing vibration levels that were too high, and it seemed that they were going to break. So the solution we came up with is we used these, this is sort of a spring. So this kind of isolates the hardware from the harsh vibration environments that the vehicle's seeing. So, and that way the electronics will survive the launch and work when they get into space. I guess it's exciting that we could be doing something new coming up here. There's talk of going to near-Earth objects like asteroids. There's talk of going to Mars and beyond. So, to do all these things, we're going to need to develop new launch vehicles, basically that can accomplish that goal. So, it is definitely an exciting time at NASA.
Biologi dan kedokteran dengan prinsip-prinsip teknik. Banyak insinyur biomedis mengembangkan dan mengevaluasi sistem dan produk seperti anggota badan dan organ buatan, instrumentasi dan manajemen kesehatan, dan sistem pemberian perawatan. Ya, banyak sekali engineer-engineer sekarang itu mempelajari medical karena dia punya tugas akhir penelitian yang diterapkan untuk healthcare. Jadi biomedic engineer itu ya harus bisa melihat, ya.
Biomedical engineering is essentially many different disciplines but with a focus on the human body. It's about using mechanical engineering, electrical engineering, materials engineering, biology, and even computer science and computer engineering to design equipment, devices, and even medicine that's used on and for the human body. So let's start with careers. A common career for biomedical engineers is making artificial limbs. These are for people who have either lost a limb or maybe need to have one amputated. A biomedical engineer would have to design the structure to be similar to a normal human limb. It should be able to deliver a similar amount of force, weigh a similar amount, and so on. They would design the mechanical structure to maintain the best quality of life for the person. For example, if the device is too heavy, it may cause strain on other parts of the person's body, which will lead to problems down the road. This is more of the mechanical engineering aspect of this major. Also, when we want to do something like make a fist, our bodies are sending electric signals to those muscles so it knows what to do. So a biomedical engineer would attach electrodes somewhere near where the limb was removed that would read those electric signals when someone wants to make a fist, for example. Then those signals would be processed and sent to a device that would tell the artificial arm to then make a fist when the person wants to, even if they don't have a hand. This is the electrical engineering and programming aspect of the major. This is also a little preview of how they do brain scans and are even making devices that are controlled using our brains. Then some artificial limbs have a rod that is inserted into the person's body for a better attachment. At the end of the rod that's inside the person's body, they will put coating that encourages the bone to grow onto the rod for a more mechanically secure attachment. Understanding those chemicals that work with the bone and the human body is the biology aspect of this major. Or let's say someone has type 1 diabetes. This means their body cannot produce insulin. So what we can do is create customized beta cells that produce insulin and inject them into the body. But unfortunately, the immune system kills those off because it thinks they are foreign. So what a biomedical engineer can do is take those engineered beta cells and surround them with a hydrogel like polyethylene glycol, and this is just a material that the immune system won't kill. So the insulin can still be supplied from the beta cells inside without being killed off. So you can see that you'll learn how different materials will interact with the body. Whereas another example of this, let's say someone suffered a bad injury where part of their skull had to be removed. What a biomedical engineer could do is create a biomaterial, which is a material that your body won't negatively react to, and this material can be used as a temporary support for the missing portion. Then over time, the bone tissue will start to grow over the material, and the material will then be dissolved and excreted by the body. Because it's a biomaterial, the human body will have no problem with it being dissolved into its system, and the missing part will then be healed over with natural tissue. The engineer would have to find a material that has a lifespan appropriate for how the injury will heal, and make sure it breaks down at the right rate. Then a current advancement in biomedical engineering is designing and printing 3D organs to be used in the human body, like artificial hearts, kidneys, and livers. They recreate a given organ cell by cell using a very precise syringe and stock of various cells needed. This is being used in the military to help soldiers who need a transplant as well. When it comes to the heart, a biomedical engineer could work on a defibrillator. These are the things you see when the doctor says clear, then provides a large shock to the person's chest to try to revive them. That's an external defibrillator, but there's also internal defibrillators. These are located inside the person's body and include sensors that detect when a person's heart needs a jump and automatically provides the shock. These can be slightly painful, but they also save lives. The sensors detect electric signals from the heart, and you know what those signals typically look like? Then if the signal starts changing in a life-threatening way, the device can provide a shock. The nerves, muscles, and heart are very electrically active in our body, so we can sense and manipulate those signals to do useful things. Biomedical engineers can also make pacemakers, which are similar in that they are internal and use small electric pulses to keep the heartbeat rhythm consistent. So if the heart starts to go from consistent beating to abnormal, the device can provide a small shock to get it back to normal. If someone has chronic pain in some part of their body that isn't related to any sort of injury, we can use devices to interrupt or add interference to a pain signal as it travels to the person's brain. This can then replace the pain feeling or greatly reduce it to help the person cope. If you want to go very specialized, you can go into neuroengineering, where you can work on things like providing electric signals to the brain of someone who has severe depression and regulate their mood. This same electrical manipulation can be used on people with Parkinson's disease or epilepsy, which both can be helped through electrical stimulation in the brain. Now the good news about biomedical engineering is that it's very broad. If you really don't like circuits or the electrical engineering stuff, you can just focus on the mechanical engineering or biology aspect, and vice versa. Now 3 of the main focuses of the major are biomechanics, bioinstrumentation, and tissue engineering. Biomechanics is the mechanical engineering focus on the body. This is for people who have an interest in the math and physics of the mechanical movement and structure of the human body and even various devices. It includes designing the structure of artificial limbs and analyzing the forces on them, as well as the forces they exert on the body. It can involve looking at the forces throughout a human body as it walks, which is useful in sports, for example. So if a transplant is needed from a sports injury, you can determine how strong and durable that support structure needs to be. Bioinstrumentation is the electrical engineering focus and designing electronics within all the equipment and devices. This is about programming the artificial limb to move based on the electric signals that are being picked up. It's about processing and analyzing signals from the heart, brain, and muscles, then creating circuits and programming devices to manipulate the signals as needed. Then tissue engineering is the biology focus. This would be like determining how to actually 3D print an organ using various cells. Then a mechanical, electrical, and computer engineer would design the 3D printer itself. Tissue engineering also includes how to make a biomaterial that can replace a certain part of someone's body without the body reacting negatively. It can be tweaking cells and generating artificial tissue. An example would be taking someone's skin cells and genetically engineering them to create artificial skin that can help burn victims. And this can even include stem cell research. So even if you don't like some subfield within biomedical engineering, it's okay because there are plenty others to choose from. Now, many students struggle between whether they should major in a specific discipline like mechanical or electrical engineering, or go into biomedical engineering. There's of course no right answer to what is the best choice for you, but here's some guidance. If you know you really want to do mechanical engineering because you like math, physics, and looking at forces, torque, stress, vibrations, or heat transfer on different devices, structures, and supports, or you know that you want to do electrical engineering because you want to work on circuits, signal processing, and programming various devices, but in both cases you want to work with the human body, then you should maybe get your undergraduate degree in mechanical or electrical engineering. The reason is because having one of those on your resume opens up many more doors than having just biomedical engineering. This is not to say biomedical engineers don't have job opportunities, because they definitely do, but it is true that electrical and mechanical engineers have more. Then you could still apply to jobs and internships in the biomedical field, but you'll only focus on the electrical or mechanical aspect of it, and maybe not so much the biology aspect. But you can still get into the biomedical sector. Then an idea is to get a master's degree in biomedical engineering. Some companies will even pay for your master's degree if you work for them. So you can get your bachelor's in mechanical or electrical, then go into the workforce, work for a year or maybe a few, then go back to get your master's. So you'll get a free or cheaper master's degree, have a guaranteed job when you graduate at the company that paid for it, you'll get paid more, and you'll have a very impressive resume that will open up so many engineering opportunities. But if you don't yet know what you're passionate about, but you know you want to work on the human body, then biomedical engineering would be a good idea, because you'll have a focus on the biomedical aspects, but at the same time you'll explore all the various support and elective classes they take, which include mechanical engineering, electrical engineering, materials engineering, and biology classes, and more. So you can get a feel for what you like. And lastly, biomedical engineering as well as biology are common majors for people who want to go into med school, because those majors will fulfill all the prerequisite classes that you need.
Engineer, ya, insinyur kimia, menerapkan prinsip-prinsip kimia untuk memecahkan masalah yang melibatkan produksi atau penggunaan bahan kimia, bahan bakar, obat-obatan, makanan, dan plastik. Mereka merancang peralatan dan proses untuk pembuatan bahan kimia, penyulingan minyak bumi, dan pengolahan produk sampingan, dan mereka mengawasi produksi.
What is chemical engineering? Chemical engineering creatively combines the three basic physical sciences, chemistry, physics, and biology, along with mathematics to address the world's needs by creating new technology and improving existing technology. But what does this really mean? It's providing clean water and sanitation to communities. It's advancing healthcare by developing drugs to cure disease. It's researching and producing foods to feed our growing global population. It's designing greener products and processes and finding new ways to generate energy. Chemical engineers are improving the quality of life in the environment we live in. Are these things that you want to achieve? You might become a chemical engineer if you like combining maths and science, upscaling your ideas, designing efficient processes, applying your knowledge, developing your ideas into usable products, taking your ideas out of the lab and into the world with real-life applications. Studying chemical engineering involves learning theory in lectures, applying what you learn in practical lab sessions, solving issues in problem classes with your peers, exploring new technologies, developing industrial strategies, understanding how to design processes and products, working in teams to solve engineering challenges, investigating the social, environmental impact of chemical engineering. By doing these things, you'll gain more than chemical engineering theory. You'll have skills in critical thinking, problem solving, project management, business insight. With these skills, you could work in industries like food, pharmaceuticals, fuels, water and sanitation, and oil and gas, preparing you to make an impact on the world. sustainably.
Engineer, apa perannya? Ya, udah tua ini, civil engineer sangat tua dan banyak karyanya. Insinyur sipil, ya, mereka juga disebut insinyur sipil. Berperan untuk merancang dan mengawasi pembangunan jalan, gedung, bandara, terowongan, bendungan, jembatan, dan sistem pasokan air dan pembuatan limbah. Teknik sipil adalah salah satu disiplin ilmu teknik tertua dan mencakup banyak spesialisasi. Yang utama adalah struktural, sumber daya air, konstruksi, transportasi, dan rekayasa geoteknik.
Civil engineering is a professional engineering discipline that deals with the design, construction, and maintenance of the physical and naturally built environment, including works like roads, bridges, canals, dams, and buildings and other facilities that are used in our daily life. Civil engineering takes place in the public sector from municipal through to national governments, and in the private sector from individual homeowners through to international companies. Civil engineering is progressing at a fast pace as are other technologies. Civil engineering has been an aspect of life since the beginnings of human existence. The earliest practices of civil engineering may have commenced between 4000 and 2000 BC in ancient Egypt and Mesopotamia, that is, ancient Iraq, when humans started to abandon a nomadic existence, thus causing a need for the construction of shelter. During this time, transportation became increasingly important, leading to the development of the wheel and sailing. The first self-proclaimed civil engineer was John Smeaton, who constructed the Eddystone Lighthouse. Civil engineering has a significant role in the life of every human being, though may not truly sense its importance in our daily routine. The function of civil engineering commences with the start of the day when we take a shower, since the water is delivered through a water supply system including a well-designed network of pipes, water treatment plant and other numerous associated services, the network of roads on which we drive while proceeding to school or work, the huge structural bridges we come across and the tall buildings where we work, all have been designed and constructed by civil engineers. Even the benefits of electricity we use are available to us through the contribution of civil engineers who constructed the towers for the transmission lines. In fact, no sphere of life may be identified that does not include the contribution of civil engineering, thus the importance of civil engineering may be determined according to its usefulness in our daily life. Civil engineers have various job specialization options. You may choose among various disciplines, depending on your personal interest. The main disciplines are structural engineering. Structural engineering involves the design of structures that should be safe for the users, be economical and accomplish the desired functions. It includes steel structures, buildings, tunnels, highways, dams, and bridges. Construction engineering. Construction engineering involves planning and execution, transportation of materials, site development based on hydraulic, environmental, structural, and geotechnical engineering. Transportation engineering. Transportation engineering is concerned with moving people and goods efficiently, safely, and in a manner conducive to a vibrant community. This involves specifying, designing, constructing, and maintaining transportation infrastructure, which includes streets, canals, highways, rail systems, airports, ports and mass transit. Geotechnical engineering. Geotechnical engineering deals with soils, rocks, foundations of buildings and bridges, highways, sewers, and underground water systems. Water resources engineering. Water resources engineering concerns with management of quantity and quality of water in the underground and above ground water resources, such as rivers, lakes, and streams. Environmental engineering. Environmental engineering is related to the science of waste management of all types, purification of water, cleaning of contaminated areas, reduction of pollution, and industrial ecology. Coastal engineering. Coastal engineering concerns specific demands posed by constructing at or near the coast, as well as the development of the coast itself. Earthquake engineering. Earthquake engineering involves designing structures to withstand hazardous earthquake exposures. Earthquake engineering is a subdiscipline of structural engineering. Apart from all these subdisciplines, there are many others too. Perks of being civil engineer. Civil engineering is an exciting profession because at the end of the day you can see the results of your work, whether this is a completed bridge, a high-rise building, a subway station, or a hydroelectric dam. Civil engineering graduates can rest assured that the demand for their expertise is constant and even growing. Because of the steady increase in civil engineering jobs in the infrastructure and construction industry in particular, civil engineering is not just a stable job, but a rapidly expanding one as well. The truth is, as long as there are structures and facilities that need to be built or constructed, there will always be a demand for civil engineers. According to statistics released by the U.S. Department of Labor, employment of civil engineers is projected to grow 20% up to 2022, faster than the average for all occupations. As infrastructure continues to age, civil engineers will be needed to manage projects to rebuild bridges, repair roads, and upgrade levels and dams.
Engineering yang berikutnya, computer engineer. Ya. Computer engineer itu berperan untuk merancang, mengembangkan, menguji, dan mengawasi pembuatan dan pemasangan perangkat keras komputer, termasuk chip komputer, papan sirkuit, sistem komputer, dan peralatan terkait, seperti keyboardnya, routernya, printernya. Insinyur komputer juga dapat merancang dan mengembangkan sistem perangkat lunak yang mengontrol komputer.
My name is Sean Hemel, and I graduated from Rose-Hulman with a degree in computer engineering. When I was an incoming freshman, I didn't know anything about computer engineering. All I knew was that it had something to do with computers, and it was a combination of electrical engineering and computer science. In that sense, I got the best of both worlds. However, computer engineers shine in a few areas that might be difficult for either an electrical engineer or a computer scientist. These areas include embedded systems, computer architecture, and digital signal processing. But what kind of jobs would it prepare you for? Well, you could design consumer electronics, such as smartphones, smartwatches, e-book readers, or maybe the next generation of Intel CPUs. Many new medical devices and scanners rely on electronics designed by computer engineers. The Department of Defense and various contractors need computer engineers to create unmanned aerial vehicle flight controls and crucial satellite communication systems. In aerospace, you might work on an autopilot for the next Boeing plane or create the control system for the next Mars rover. Finally, in the world of automation, computer engineers are writing low-level software for Amazon's warehouse robots that help pick and deliver goods for packaging. So, what kind of classes will you take to become a computer engineer? First, you'll need a healthy dose of math. Particularly, you'll need calculus, differential equations, and some probability theory. From the computer science side, you will likely learn a couple of programming languages. These languages allow you to write code to tell computers what to do. You might start with a low-level programming language, like C, to teach you the underlying concepts of how an operating system works. You might practice what you learn with a project, such as writing a device driver for your computer to, say, respond to mouse clicks or read from a USB drive. You will also learn a high-level programming language, such as Java or Python. These are application-level languages that teach you higher-level computer science concepts, such as object-oriented programming and algorithm design. Projects might include writing a smartphone app, creating a simple game like Flappy Bird, or searching through a database for customer information. You will be introduced to a variety of algorithms, which is just a fancy way of saying steps required to solve a problem. Google, for example, uses a very complicated algorithm to crawl through the internet and sort your search results, starting with the most relevant. You will learn how to develop algorithms like this and analyze them for execution time and efficiency. From the electrical engineering side, you will usually start with basic circuit design, which includes creating and analyzing simple circuits with passive components like resistors, inductors, and capacitors. Labs might include designing circuits on paper, building them on a breadboard, and then testing their operation with an oscilloscope. Later classes will introduce semiconductor components like diodes and transistors. These lay the foundation for courses in digital circuit design, including logic gate operation, Boolean algebra, and binary. These classes will lead into computer architecture, where you will learn how a computer works, like really works. Often, you will be required to design your own computer processing unit, or CPU, by the end of the class. With these foundations, you can then move into the more specialized areas of computer engineering, and this is where the fun begins. You will likely take a class in embedded systems, which are essentially tiny chip-sized computers with processors known as microcontrollers. Knowing the basics of electronics and low-level programming allow you to work with microcontrollers, which can be found in smartwatches, drones, and modern thermostats. If you have heard of Arduino, it is a type of embedded system. Finally, you'll be required to take at least one class in signal processing, which is the analysis of how electrical signals change over time. Here, you will be introduced to communication systems and filters. Trying to transmit data over long distances, say images of Mars from the Curiosity rover, requires a lot of engineering, and signal processing is just the beginning of these types of communication systems. Computer engineering also puts you in a good place to study robotics, as most robots rely on embedded systems for their brains. And these are just some of the things that computer engineering lets you do. It gives you a taste for electronics as well as programming, but it also allows you to specialize in some fields that develop exciting new technologies that affect our everyday lives.
Electrical engineer. Electrical engineer itu berperan untuk merancang, mengembangkan, menguji, mengawasi pembuatan peralatan listrik. Beberapa peralatan itu termasuk motor listrik, kontrol mesin, penerapan, perangkat transmisi yang digunakan, ya, penerangan dan kabel di gedung, radar, dan sistem navigasi, sistem komunikasi, dan pembangkit listrik dan perangkat transmisi yang digunakan oleh perusahaan listrik.
Electrical engineering is a very broad major that encompasses a lot of sub-disciplines. Within the umbrella of electrical engineering, there are fields like RF, which is basically wireless communications, where you could work on satellite communications for defense purposes so the signal cannot be jammed by an enemy. There's electronics, where you could design the circuit boards within computers or phones, or the control systems within autonomous vehicles, or the circuitry in a prosthetic arm. There's power, where you'd work with high voltage systems and delivering or generating lots of electric power. That could include working at a power plant, working with solar panels, or something like electric motors and regenerative braking, where, like in certain electric vehicles, when you take your foot off the accelerator, the motor turns into a generator due to changing speeds of certain components within the system, and then the kinetic energy of the wheels is used to generate electricity that can be stored for later use. There's controls where you'd work on things that have some sort of electrical feedback, like propulsion systems in various aircrafts, all the way to your cruise control, where your speed is monitored, then depending on what it receives, the system turns the wheels faster or slower accordingly, which then affects your speed, which is then fed back into the system, and this control loop continues. There's instrumentation, which deals with designing sensors and equipment to measure physical quantities like pressure, temperature, motion, position, and so on. You could design motion detection sensors for a security system, GPS for aircrafts, or all the sensors in your car that have to analyze fluid levels, temperatures, battery voltage, anti-skid braking system, or more advanced systems for driverless cars. These types of electrical engineers often work with controls engineers, because after all, a controls engineer could design a great system to control the speed of an aircraft, let's say. But if all the sensors cannot accurately determine the speed, air pressure, and so on, the control system is basically no good. There are many of these fields, but the last one I'll explain is signal processing. This is simply about the manipulation and analysis of signals. Signals being essentially functions that convey some sort of information. Maybe you have this sinusoidal voltage at some frequency, and then a sensor in the system causes an increase in the frequency, and that frequency change is related to the temperature that the sensor is picking up. Now that changing voltage or signal contains information about the temperature in the room that we could convert to text on a screen, let's say. But when it comes to signals in general, you might have to amplify them, like for an earpiece, or filter them where there's background noise, and much more. and this can apply to radio signals, cell phone signals, radar, missile guidance systems, speech, image, or video processing that all involve signals that need manipulation. There's GPS signals, noise-canceling headphones, and of course, way more. Okay, now I've already thrown a lot at you to encompass a lot of what you can do as an electrical engineer, and as you can see, it's very broad. It's not just one thing. As in, two people who majored in electrical engineering, as with many other engineering disciplines, could be in two totally different fields or careers and have very little knowledge about each other's work. And this is also not about being an electrician, by the way, which is a common misconception. Electrical engineering is not where you go in and install or repair electrical systems in people's houses or in offices and so on. But if you're debating picking this as a major, all the fields I discussed could seem like a lot, and you may be thinking, wait, what does an electrical engineering major look like and what can I expect? And that's what we'll go into now. While all schools are a little different, a typical electrical engineering curriculum consists of a few circuit analysis classes to just get you started, digital design, a power engineering class, continuous time signals and discrete time signals, which are what get you started with analog and digital signal processing respectively. You'll take a controls class, a communications class, which you'll learn the basics of FM and AM radio, a basic electronics class, which likely is followed by analog and digital electronics, some electromagnetism courses, which are basically physics classes, and a microprocessor class. There are some others you'll take, and this doesn't cover the math or physics classes that you'll see, but these are the big major classes to expect in undergrad. Don't worry about what they are for now, but just know this is pretty typical. Now see how regardless of who you are, you'll take some classes on most of those subdisciplines I mentioned earlier. You got your power class, you got some signals classes, wireless communications, controls, and so on. As an undergrad, you get exposure to a lot of foundations of electrical engineering, and you become well-rounded, but you don't become an expert in really any field. That's where masters and PhDs come in, or just simply working in a field for many years, of course. You will be taking electives in the subfields you're most interested in though towards the end of college, so you will gain a little more mastery in those classes, which diversifies you and your resume from others, but it's not the bulk of your curriculum. But now let's go through these a little. The first are the circuit analysis classes. Now if you've taken physics classes in high school, maybe you've seen the basics of resistors, capacitors, and inductors. And you're going to learn how to find the voltage and current in circuits that contain these three components, first starting off with just resistors though. In the real world, circuits are normally extremely complicated, and engineers usually use software and simulations to analyze the circuit. But in school, you gotta learn the basics of voltage and current in a circuit. For those who may be unfamiliar, if you imagine a network of pipes, you could use a pump that creates a pressure difference and causes water to flow around and through all the pipes. If the pipes are skinny, let's say, it'd be harder for water to flow through them. And if they're thicker, then of course it'd be easier. Well, in a circuit, the voltage from maybe a battery is like the pressure difference from the pump. The current or electron flow is like the water, and the resistors are like the pipes. High resistance is like a skinny pipe, harder for water or the current to go through. Your electronics work for many reasons, but mainly it's because electrons are flowing through the device. In school, you learn techniques to find the voltage difference across various resistors, just like there'd be some pressure difference across each individual pipe. Circuits classes are a lot of systems of equations, just like you learned in school before, but more variables usually, and instead of x and y, it's usually v and I for voltage and current. And to begin, all the circuits have a constant voltage as an input, like a 9-volt battery that is not changing. Then in a second level circuit analysis class, you get into capacitors and inductors. You'll use those same circuit analysis techniques, and the voltage source will still be constant like a battery, but current and voltage in the circuit across those components change in an exponential way, like charging up a capacitor to a max voltage. In order to find that max value, or the time it takes to charge up to, let's say, half the max value, you'll use circuit techniques to find the resistance in the circuit and so on. Then you'd quickly move on to AC circuits, or alternating current, where the input voltage is no longer constant, but sinusoidal and changing over time. For these circuits, there is some more complexity added, where a capacitor or inductor in a circuit with a resistor causes the voltage to change its amplitude, but also shifts it. The capacitor or inductor can change the phase of the voltage within the circuit. The math behind this actually involves imaginary numbers. That square root of -1 you learned in high school actually has a ton of applications, and this is one. And it's not because current or voltage are imaginary, but using imaginary numbers just makes the math work when it comes to changing the phase or theta offset in a cosine or sine function. Don't worry about all that now, but it is something you will learn. There's of course plenty more in the basic circuits classes, but let's move on to the signals classes. These are essentially math classes and will be one of the most math intensive electrical engineering classes you'll take. Before this, you've dealt with constant voltages and then sinusoidal voltages, but what about, well, everything else? You could have a triangle wave, a square wave, or some really complicated and messy voltage, which is what real-world signals can be like. So what happens if you put those into a circuit? Well, in this first signals class, you'll learn something called the Fourier series and Fourier transform, something very important in physics, engineering, and applied math. This says that any function can be made up of a bunch of cosine and or sine functions added up, often an infinite amount. Here we can see just a plain square wave. But if you have a sine wave and add it to another, and then another, and you keep going, picking sine waves with the right amplitude and frequency, it will approach that square wave. In this class, you will use some calculus and some new math concepts to find those frequencies and amplitudes of the sine functions that make up some other function. So now if we put a square wave into the circuit and want to know what the voltage and current will look like, we can mathematically model it like putting in a bunch of sinusoidal waves of different amplitudes and frequencies, which you will already have under your belt. You will learn lots of mathematical techniques to simplify this for you. Now, two specific types of signals you see here that kind of look sinusoidal but not really are AM and FM radio signals, which brings us to your wireless communications course. This class is not about physics, but just more of the math behind specifically AM and FM signals. If you look at a simple AM signal, you'll notice the amplitude oscillates up and down, and if you look at an FM signal, the frequency oscillates throughout the wave. By making the signals look like this, it causes the frequencies to move up to some specific unique center frequency, like 94.1 megahertz that the radio station transmits at. This is what the station 94.1 FM is, just that station transmitting at that specific frequency. Yes, it's more complicated, but that's the general idea. Without that manipulation, you could not wirelessly send those signals for people to listen to in their cars. You'll learn why this has to be done and all the math behind that in this class. Then when you take your electromagnetism courses, it will be pretty much all physics and involve a good amount of calculus. You'll see how when you have a change in current, it creates a magnetic field around it, which then in turn creates an electric field around that, and this continues and this propagates as an electromagnetic wave, because its electric and magnetic fields are coupled together. You'll learn a lot about what those waves do when they interact with objects, like what if they hit some metal barrier, or they encounter water, how far could they penetrate if there was a receiver at some depth. You'll also learn about transmission lines, which aren't probably what you think of. The ones you learn in this class are cables that handle very high frequency signals that oscillate back and forth very quickly. You cannot just put a very high frequency signal into a normal circuit. Issues come up simply due to the laws of physics, and you'll learn about all that as well. Many of your other classes tell you about how to analyze signals and manipulate them for various purposes, but this class really teaches you about the physics of the waves so you can understand things like how a wireless signal will be affected as it travels through Earth's atmosphere when we have to communicate with a satellite, for example. Then moving on, in your electronics classes, you'll finally learn about the transistor. There are billions of these in your laptop and millions in your phone to make them work. There are lots of kinds of transistors, but to simplify, in a circuit, the current often flows down here, and a little flows in here, and they combine and flow out here. You'll learn more circuit analysis techniques to analyze voltage and current in these circuits as always, but the thing is, by changing this voltage on the transistor, you can control how much current flows through the transistor, meaning the transistor can essentially act as a switch. It can allow current to flow, which is basically like the transistor being on, and it can shut off current flow, which is it being off, of course. This can create a high voltage like 5 volts and change it to a low voltage like 0 volts. This is the binary or ones and zeros that are really under the hood of your computer. You will learn about making circuits that can switch quickly and efficiently in your digital electronics class. Analog electronics is more about using transistors to amplify a voltage, which is their other main application, where amplification would of course be needed for music or hearing aids as an example. Now there are of course a few more classes I won't go into as much detail on, like in digital design you learn about logic gates, which take ones and zeros as inputs and output ones and zeros as well. The different gates output different things based on the inputs. Zooming into these is what digital electronics is, where you see the circuits that convert the high voltages to low voltages or vice versa. But in this class, it's zoomed out looking at the ones and zeros and making circuits with these logic gates. In the power class, you'll analyze electric motors and generators and do circuit analysis with those. You'll do labs where you work with much higher voltages than normal, like over 100 volts. You'll see how much power is dissipated in resistor networks and so on. And the controls class has to do mainly with systems that involve some sort of feedback. You'll look at things like stability, because if you're constantly feeding information back into your system and something goes wrong, it could continuously be maybe amplifying some output, which will lead to issues. You'll also see a lot of these graphs where you have some target output signal, and in some cases there will be overshoot, and then the signal will settle back to that target after a certain amount of time, versus just slowly charging up. You'll mathematically find that overshoot, how to minimize it or avoid it, and more. Hopefully that gives you a good overview of the major, but due to time I'm going to stop there. However, this was my major, so if you want information on specific labs you'll do from freshman to senior year of college, more specifics on the concentrations, their applications, and previous senior projects, what math classes you'll take, how my first job or internship was, and so on, they're all on this channel, and I'll link some below. So if you're looking for even more depth, give those a look. Otherwise, hopefully this was a good foundation. Some schools, especially outside the US it seems like, offer majors in electronics engineering or telecommunications engineering, or some combination, but that would be for another video. This was just on electrical engineering, which encompasses lots of subdisciplines that you saw. Every school will be different of course, but you can expect most of what you saw here. And lastly, as you can see, electrical engineering can get you jobs in the aerospace field, biomedical field, at tech companies, defense companies, in the energy sector, in robotics, and so much more. But so can plenty of other engineering disciplines that are also broad. So if you're considering this major, make sure this is the type of engineering you want to do specifically when it comes to whatever field or sector you may want to go into. Otherwise, I'll end there, and if you liked the video, don't forget to comment, like, and subscribe, and I'll see you all next time.
Insinyur teknik lingkungan menggunakan prinsip biologi dan kimia untuk mengembangkan solusi bagi masalah lingkungan. Mereka terlibat dalam pengendalian polusi air dan udara, daur ulang, pembuangan limbah, dan masalah kesehatan masyarakat. Insinyur lingkungan melakukan studi pengelolaan limbah berbahaya di mana mereka mengevaluasi pentingnya potensi bahaya dan mengembangkan peraturan untuk mencegah kecelakaan.
What is the first thing you think of when you hear the words environmental engineering? Save the trees? Save the fish? Recycling? Have you ever wondered what environmental engineers do? Environmental engineering is the study of the effect of human activities on the environment and the use of engineering principles to improve and maintain the environment. The United States Environmental Protection Agency has identified 10 issues of concern in this matter: air, water, waste, land and cleanup, health and safety, climate change, green living and sustainability, emergencies, chemicals and toxins, and pesticides in agriculture. By focusing on these issues, environmental engineers improve and maintain the environment for the protection of human health and ecosystems.
Me too?
Yes, you too. To see how important environmental engineers are to our life, let's look at our own daily routine. When you wake up in the morning, what is the first thing you do? You wash your face, brush your teeth, and you use the restroom. To do all of these activities, you need clean water. Environmental engineers clean river water and groundwater to provide you with safe drinking water, which you use for all your activities throughout the day. What happens to that water that you use? In a day, each of us generates 265 to 375 liters of wastewater. All of it has to go somewhere, right? All this wastewater is sent to treatment plants near your house. Environmental engineers design these plants to clean millions of gallons of water each day in order to maintain water quality of rivers and oceans. Moving on. Now that you're dressed to go to school, you go to the kitchen and eat breakfast. You throw away any leftovers and trash, cereal boxes, wrappers, paper towels. Where does it all go? The trash you generate is collected from your house and is either recycled, composted, incinerated, or buried in the landfills. There are more than 3,000 landfills in the United States that are specially engineered to hold tons of solid and hazardous waste generated by people and industries so that toxic chemicals in the waste do not pollute the soil. Okay, let's go back to your morning routine one last time. You finish breakfast and you're ready for school. You get on the school bus. You may have noticed that buses spit out smoke when they run sometimes. The smoke contains gases such as carbon monoxide, carbon dioxide, which deteriorate air quality. The air quality in your city is monitored by environmental engineers. They also make technologies to take out a lot of the harmful chemicals from the smoke so that the air is healthy, safe, and breathable. Okay, so far we've talked about how environmental engineers affect our daily life. Clean water, clean air, and no waste. Are there other ways that environmental engineers help you? Of course! Remember that environmental engineers study anything that could affect the environment and try to make the environment better. In many places, the air, soil, and water is already filled with harmful chemicals that can hurt animals or humans. Environmental engineers use advanced technologies to research treatment methods to take these chemicals out of water, soil, and air to make the environment safer for humans and animals. Another way environmental engineers help people is by improving sustainability and researching alternate energy. They closely monitor the health of the environment and study the risk posed by any natural and industrial disasters to the environment. These are just some of the ways environmental engineers help protect public and ecological health. Think about your life. What are some ways you know environmental engineers help you?
Engineer berperan untuk menentukan cara paling efektif menggunakan item dasar produksi, manusia, mesin, material, informasi, dan energi untuk membuat produk atau menyediakan layanan. Mereka prihatin dengan peningkatan produktivitas melalui pengolahan orang. Metode organisasi bisnis dan teknologi para insinyur ini mempelajari persyaratan produk dan kemudian merancang sistem manufaktur untuk memenuhi persyaratan tersebut.
Design can be defined as bringing an idea of a product into reality, and manufacturing is bringing a design into life.
The design engineers are the engineers who basically specialize in designing products. They use three-dimensional computer-aided design software in which they learn how to make parts in virtual reality. And then manufacturing engineers, on the other hand, are the ones who know how the manufacturing processes work, and they're able to interface with the shop floor and the people in the manufacturing sector to get a machine made.
What's unique about design and manufacturing is that you tackle unique and challenging problems, and the uniqueness of the problems gives you an edge. It makes you basically valuable to a potential employer because of the rarity of your skills.
Through the learning experience, both in and beyond the classroom, students can acquire knowledge and skills to succeed academically, and also they can develop their personal and academic identity here.
The Alberta Learning Factory is a setup where students, no matter if they are undergrad or graduate students, learn about all the different stages through what a product needs to go through when it's manufactured in a real environment. The supervisors in the Design and Manufacturing program allow you to have leadership roles and professional development that will enable you to focus your career. The Design and Manufacturing program allows definitely to have interaction with very different types of engineering and engineering languages.
Here in the Department of Mechanical Engineering, because we have a lot of unique advanced equipment, we provide great opportunities for experiential training to our students.
So that gives us and our students chance to access state-of-the-art facilities, state-of-the-art equipment at the industrial partners sites as well.
It has given these students practical, hands-on training with for-profit or non-for-profit companies or government research institutes that then give them the skills that are immediately transferable into the jobs that they will decide to take on.
I would definitely recommend students around the world to come and join mechanical engineering department to get the exposure they're looking for.
Insinyur material terlibat dalam pengembangan, pemrosesan, dan pengujian material yang digunakan untuk membuat berbagai produk, mulai dari chip komputer dan sayap pesawat hingga tongkat golf atau ski salju. Mereka bekerja dengan logam, keramik, plastik, semikonduktor, dan komposisi untuk membuat bahan baru yang memenuhi persyaratan mekanis, listrik, dan kimia tertentu.
Materials are all around us. It makes up everything that we use from day to day. But one thing a materials engineer will do is try and make those materials better.
I think materials science and engineering is basically when engineers take materials that are in everyday use and we look at it in the microscopic scale and the atomic scale and then try to enhance them into like our macro scale everyday materials that we use.
You use materials everywhere. We're currently standing in a building made of materials, made of concrete and steel, and all of those had to have been studied at some point in order to know that they are the most structurally sound materials for this application.
Everything in the world is made up of materials, right? And those materials, what we see macroscopically, like a piece of steel, just looks like one hunk of steel to us, but actually there's a bunch of little particles that it's made up of, and how those are arranged changes how strong the steel is, how easy it can bend, when it melts and things like that. So material science and engineering is actually controlling that so that we can change how strong the steel is or anything. We also do polymers and plastics, ceramics, and electronic materials also.
Using science and engineering to make everything better in our world.
We can look at a failure of a piece and determine why it failed, how it failed, if a similar piece that's in use will fail.
The more efficient we can make batteries, it'll help consumers a lot.
We need things that are more efficient with energy, we need things that are recyclable, or even such things as being tougher, stronger, more resistant to corrosion, environmental things. So it can span pretty much all spectrums of industry out there in the world.
We have higher demand for electronic components that need to be smaller and lighter. So you need to come up with new materials that can handle such capacities.
There's only a certain amount of different elements in the earth. And a lot of things that we use to make things like TVs and electronics and things like that are limited. So if we can figure out how to recycle them and reuse that, it'll be more cost effective.
Another realm of materials that's going to, I think, be on the rise in the future is going to be multifunctional materials.
Life cycle, the whole system. What's going to happen to this in the end? Things like plastics and stuff, a lot of people are worried about landfills and things like that they don't break down very well. So there's people working on polymers that are made out of biomaterials like corn and potatoes and things like that will actually biodegrade.
I feel like I have so many options to choose from and so many different areas I could go to.
To make technology greener and as well keeping it friendly enough for everybody to still want to use in everyday applications and not make it a big hassle for everybody to become a green society.
Ames Lab is located on the edge of campus and it allows a lot of students to have research positions with professors or scientists to allow them also the opportunity.
The visit I had to Iowa State sold me. The department up here is one of the most up-to-date, I think, advanced laboratories we have for materials engineering, and then the community we have, the access we have to professors and research and things, is just an opportunity you can't pass up.
Nuclear engineer berperan untuk mengembangkan proses, instrumen, dan sistem yang digunakan untuk memperoleh manfaat dari energi nuklir dan radiasi. Mereka merancang, mengembangkan, memantau, dan mengoperasikan pembangkit nuklir untuk menghasilkan tenaga listrik. Mereka mungkin bekerja pada siklus bahan bakar nuklir, produksi, penanganan, dan penggunaan bahan bakar nuklir, dan pembuangan limbah nuklir dengan aman.
Next up, it's nuclear engineering. Now, when anyone mentions the word nuclear, it's as if it already has a name for itself, and not a good one. Uranium, plutonium, weapons of mass destruction, you've probably heard of these. But in actual fact, nuclear engineering is much bigger than this. If engineers and scientists play their cards right, we could be producing energy in a far more sustainable way. Okay, let's start big. Nuclear weapons. I know what you're thinking. Why would anyone want to be involved in this? And we understand. But let's put aside the politics for the sake of science and engineering and just say countries mainly use them as a deterrent. Yes, a deterrent. A little naive, but let's go with it for now. Besides, most countries have signed a non-proliferation treaty. Basically, they're not allowed to test their weapons. But what about deep underground? Surely they can test it there. Well, no. They have monitors everywhere. You'll be detected by other countries in minutes, if not seconds. So, if we can't test the weapon in the desert like they used to, or deep underground, how do you know if what you have even works? Well, you have to test individual parts of the weapon, or even simulate what it would be like. Like using lasers that can heat objects to temperatures hotter than the centre of the sun. Why? Well, when the weapon goes off, you can expect temperatures to exceed tens of millions degrees. Now that's far hotter than the centre of the sun. And this type of research is also being used to better technology, helping mankind move into the future. But how exactly? How would this help anyone? Well, through something called fusion, but we'll get into that a little later. For now, let's talk about fission and how it produces energy for nuclear power. So how does it work? Well, by splitting uranium atoms, you can produce a tremendous amount of heat. Now, when this is contained correctly, you can circulate water around it, which of course turns to steam with enough heat. Now with this steam, you channel it through a turbine, and voila, you guessed it, electricity. Now, this sounds simple, but the complexity begins when making this process safe. We've had two pretty bad accidents in the past, Fukushima and Chernobyl. These both caused thousands of casualties and affected millions of people. There are some good videos on YouTube that explain what went wrong on those days, what nuclear engineers have learnt from it, and ultimately how we can ensure nothing on this scale happens again. Nuclear energy is favoured today because it doesn't release any greenhouse gases, but instead produces radioactive waste. Now this is deadly stuff and needs to be stored deep underground for some years before it's considered safe. So this takes us back to our earlier question. How can we take mankind into the future? Instead of splitting atoms, what if we fuse them together? Well, our sun does exactly this. Remember when we briefly mentioned fusion? Well, this is it, a new type of nuclear power. With very little waste and almost free energy for everyone, the possibilities for this is unreal. What we learned from simulating nuclear explosions can bring us closer to understanding fusion and put this power on the grid, making these possibilities real. Aside from trying to bring free energy to everyone, nuclear engineers can also be found in the medical industry. I know what you're thinking. Weapons of mass destruction, Fukushima and Chernobyl, how could they possibly operate in the medical industry? Well, they continue to look into how small controlled amounts of radioactive material can help patients, like making cancer show it better on scans, or even treating it altogether. So yeah, if you were to stare at a block of uranium-235, you're definitely going to run into a few problems. But this whole stereotype of nuclear engineering being bad just isn't the case. When engineers safely channel it correctly, it can do a lot of good. In fact, very soon we'll be pretty reliant on it. And this is really what engineers do. They take these incredible principles and make them work safely. You know, we can't let anything go wrong. You remember when Otto Octavius messed up his calculations? Yeah, you really don't want to end up like him. We hope you would have subscribed by now. But seriously, if you didn't like the video or wanted to do something else, drop us a message, leave a comment, you know how it works.
Tingkat internasional yang juga bisa mereka tuliskan hasil-hasil karyanya mereka, ya. yang di Electrical Engineering IEEE. Jadi kita bisa masuk ke sana, lihat, ya. Kemudian semua hampir punya asosiasi.
We are often asked to tell what is the IEEE. We will try to answer that question, but it's neither an easy nor trivial task to do. IEEE is more than just an organization. From the user's perspective, it is a tool for professionals, a social network, and a source for relevant knowledge. From the contributor's perspective, it is a collaborative platform made by engineers, professors, and students, and it all started back in 1963 with the merging of two institutes. Presently, IEEE is a worldwide organization involving thousands of members united in fostering technological innovation and excellence for the benefit of humanity. The growth of IEEE led to a division in 10 geographical regions. USA alone, the birthplace of IEEE, encompasses Region 1 to 6. Canada is designated as Region 7, whereas Region 8 includes Europe, Africa, and Middle East. Finally, Region 9 includes all countries of Latin America, and Region 10 covers Asia and Pacific countries. This geographical arrangement is complemented by 38 common or cross-cutting societies, offering services to members of all regions within specific fields of interest. This allows optimization of resources and energies, as well as acceleration of knowledge sharing, either among regional neighbors or between colleagues from different regions, as long as they have similar interests. Those societies are grouped in 7 technical councils to enhance coordination for specific technological areas and to support organization activities beneficial to society's members. The 10 regions have 333 local sections where members pool their energies to launch and coordinate activities. Student branches are an important part of local sections. In short, they are student groups dedicated to bring up activities related to engineering and technological innovation. There are more than 2,000 student branches in about 80 countries, what shows how relevant this component is for IEEE. Besides student branches, local sections may include affinity groups. These are non-technical units dedicated to support and coordinate special purpose initiatives. There are presently more than 530 of those initiatives. Technical units are called chapters, made up with members of one or more society, motivated by a common interest or objective. There are more than 2,080 chapters in operation. Either affinity groups or chapters can be developed within the scope of student branches. IEEE is the world's biggest professional organization, only based on the work of volunteers from all ages and engineering sectors that give their best to contribute for the technological progress for the benefit of mankind.